So recently I went to the third week of the summer workshop at Simon Center for Geometry and Physics. This workshop is held every year and it starts from late July and goes to mid-August. And this was the 23rd year for this workshop. So this year, the theme of this workshop was theory and experiment and the emerging new physics. So therefore, a lot of talks this year were experiment-driven talks. So mainly I went to this workshop because I wanted to see what kind of work are people doing on the experiment side and what are the main problems that need to be solved, and if there is anything that the theory people can do in order to explain the things that experimenters are not able to explain using their data. And the second reason why I went there is that I wanted to meet people who are working on similar things that I'm working on so that I can exchange ideas with them and potentially start collaborations with some of them. So this summer workshop is organized by Kumrun Wafa, and the local organizer is Martin Rocek, who is a professor at Stony Brook University. So in the last week of this workshop, when I was there, the speakers included Juan Maldacena from Princeton. He's a very well-known physicist. Adam Rees, who is a Nobel laureate in physics from 2011. Bryce Sir from MIT, Vivian Miranda from Stony Brook University, and Patrick Mead, who is also from Stony Brook University. So I went there with my advisor and one of my colleagues. We started from Albany and we drove to Stony Brook University, which is in Suffolk County in Long Island. It takes almost 4 hours depending on the traffic. So I stayed in a Hilton hotel there, which is in Stony Brook University. And in Simon Center, you were given an office for the length of your stay. And one very interesting thing is that my office was 2 offices away from John Pardon, who is a very recent Fields medalist. So that was very interesting to him. So the room that you get in Simon Center comes with your name on the side of the door. And on the top of that nameplate, there is a very small chalkboard, and you can write something funny or physicsy there, whatever you want to write there. But some people also make drawings, very cool drawings there. For example, look at this drawing that I found on the top of someone's nameplate this year. And I found it to be cute enough that I took a picture of it. So every day in this workshop starts from the breakfast. It goes for almost an hour. It starts at 9 a.m. and goes until 10 a.m. And at 10 a.m., the talk of the day starts. Every day has a single talk. There are no more than 1 talks per day. Now, every talk has 1.5 hours. But 1 hour of each talk is delivered after the breakfast. It starts at 10 a.m. and goes till 11 a.m. Then there is a break in which people can go to the cafeteria and have some coffee or tea. And after half an hour, people come back to attend the last half hour of the talk. And after the last half hour of the talk, we go to lunch. Lunch lasts for almost an hour and a half or something like that. And then people can go to their offices and they can talk to each other or they can work on whatever they are working on. And Simon Center has great places to work. They have great spots. For example, this spot that I just really, really loved when I was there. And they also have many, many chalkboards on the walls, in the halls, in the rooms. So you can always find a chalkboard close to yourself if you want one. In the evening, around 3:30 p.m., there is another tea session. So people can come back to the cafeteria and exchange ideas and talk about what they're working on. And after the tea break, you can either go back to your offices and continue to work on what you're working on, or you can go back to your hotel. So on Monday, this is what happens. But on Tuesday, there is an additional activity that happens, and that activity is the concert. So Simon Center has a concert series, and they continue to invite different kinds of musicians to perform in front of an audience to get exposure. So when I was there last week, the concert was a jazz concert, and it was great. On Wednesday, there is a beach talk. The talk happens on the beach. We all sit in a bus and we go to the beach to attend the talk. After the talk, we have lunch. And after the lunch, you can either put on your bathing suit and go to the ocean, or you can just sit outside and enjoy the weather and nature, or you can come back to the hotel. So I prefer to come back to the hotel after the lunch. On Thursday, we have the conference dinner, and this conference dinner happens at Martin Rocek's house, who is the local organizer of this workshop. So in this gathering, we just hang around, eat food, and talk to different participants of this conference. Also, there are people who are playing piano and guitar, so there is a background music that you are always hearing whenever you are talking to people here. And after the dinner, Kumrun Wafa, who is the main organizer of this workshop, thanks Martin Rocek for his hospitality over the years, because this has been happening for 23 years. So we all get together where Kumrun thanks Martin Rocek and we take part in this ceremony. So Friday was the last day of the workshop. So on that day, after the talk finished, we drove back to Albany. It again took 4 hours. So what kind of topics were discussed in the last week of this workshop? So the first talk was delivered by Juan Maldacena, and he talked about string amplitudes and their relation to matrix models. So matrix models constitute a very interesting topic in the field for 2 decades now, because they are dual to, for example, JD gravity, which is a very interesting gravitational system in 2 dimensions. And also you can describe M theory in terms of a matrix model called BFSS. So this is the matrix model that Maldacena was talking about. The talk on the second day was delivered by Adam Rees, who is a Nobel laureate in physics from 2011. So he talked about Hubble tension. Now, what is Hubble tension? Hubble tension is the fact that when we try to measure the Hubble parameter in cosmology, which is the parameter that tells us that how fast is the universe expanding, if we try to measure that parameter through 2 different ways, we get different answers. One of those ways is to use the cosmic microwave background, which is a relic of the early universe, right? So the data that is used to measure Hubble through cosmic microwave background radiation comes from an experiment called Planck, right? That experiment happened in 2010s. And that particular experiment gives us the value of Hubble parameter around 67. But there's another way in which you can measure Hubble parameter, and that method uses type 1 supernova. So type 1 supernova happen in the late universe, not in the early universe. So when we use type 1 supernova in order to measure Hubble parameter, we get an answer which is very much dependent on the model and the kind of analysis that you are doing, but it goes between 72 and 75. It doesn't come below 72. So you can see that we have 2 different kinds of methods, and they are giving us different values for Hubble constant. Now they're very close together. Of course, they're close together, but the difference between them shouldn't be that big. And therefore, there is something fishy going on. And this particular story is called Hubble tension. Tension means that there is a tension between these 2 kinds of methods. So Adam Rees talked about Hubble tension and what can be the possible reasons why Hubble tension is there and what can we do in order to solve this problem. So Bryce Sayre discussed cosmic microwave background radiations and possible distortions that one can find in the spectrum of cosmic microwave background radiations. If you look at the spectrum for cosmic microwave background radiation, it looks like a black body radiation spectrum because we expect cosmic microwave background radiation, or CMB, to radiate like a black body, and its spectrum should correspond to the temperature that it has. The temperature turns out to be 3 Kelvin, and the spectrum of CMB follows the theoretical prediction very well, and that prediction is nothing but the black body radiation curve. But the question that you can ask here is that, are there any kinds of distortions that you can see in this spectrum? And it turns out that there are some possibilities for these distortions, and these distortions are called mu-type distortions and Y-type distortions. And these distortions come from particular kinds of processes. One such process is nothing but the Compton scattering. For example, the mu-type distortions come from Compton scattering. And there are Y-type distortions as well that can come from other processes. So Vivian Miranda discussed Hubble tension again, and she discussed different approaches that one can use to hope to resolve Hubble tension. But it turns out that even if you resolve Hubble tension, there are other kinds of tension that you can turn on. For example, there is a tension for the parameter tau, and tau is called optical depth. So if you resolve Hubble tension, you can turn on tau tension or some other kinds of tension. So the problem is not that simple. You don't just have to solve the Hubble tension, you also have to solve other kinds of tension in order to have a consistent framework. So that's what her talk was about. On the last day, Patrick Mead discussed high energy accelerators and can we continue to go to higher and higher energy accelerators. He also discussed the problems that we can face if we continue to go to higher and higher energy accelerators. For example, the cost, the energy budget, the higher magnetic fields which are required to have these accelerators, and also the big size. If you want to go to the Planck scale, the size of the accelerator has to be something like 10 to the power 3 light years, which is just absolutely crazy. So of course, we're not going to keep building bigger and bigger accelerators. One thing that he discussed, and that thing has been discussed for quite some time now, is the muon accelerator. The muon accelerator has some special challenges that comes with it. One problem is that when you produce muons, and muons are mostly produced by the decay of pions, the question that arises here is that since muons live for a very small time, like 2.2 microseconds in their own reference frame, how can you make sure that in this very small time, you can make a collimated beam of muons and put them into a hairline beam? Hairline beam means that a beam whose thickness is like the thickness of a human hair, because that's what you require for these kind of experiments. So this is one big challenge with muon accelerators. This was discussed in Patrick's talk, and also other accelerators. For example, if you have a proton-proton accelerator and if you have an electron-positron accelerator, then what kinds of challenges would you require to overcome in order to have these kinds of accelerators? So this was my experience at Simon Center this year. I hope you got something out of this video, and I'll see you in the next one. Thank you. So if you like this video, give it a thumbs up and consider subscribing, and the YouTube algorithm thinks that you will also like this video.